then suppose we are able to compute all of the eigenvectors and generalized eigenvectors. This leads us to yet another decomposition. And really the best one for clearly describing the whole eigenpicture, I guess. Okay. Now, the Jordan canonical form, and this exists for any n by n matrix A. X, J, X inverse. X has, so it's an invertible matrix. Columns are the eigenvectors and the generalized eigenvectors. So all of them are arranged to give you X. Okay. Now, J has a very interesting structure. It is block diagonal, and we'll call the blocks J1, J2 up to Jp for however many blocks we have. And then each of these is called a Jordan block, and each of these blocks has this structure. It is upper triangular, and it has n eigenvalues, same eigenvalue, all the way down the diagonal, and then it has ones along the super diagonal, and everything else is 0. Now, how does this Jordan form relate to the eigenvectors and generalized eigenvectors? So the number of blocks, P, is equal to the number of linearly independent eigenvectors. So if we have n linearly independent eigenvectors, we have n blocks, each of them is 1 by 1. So that's just the diagonalized case again. Now, the number of Jordan blocks, so the J sub I here, that feature a particular eigenvalue on the diagonal is equal to G sub I. The eigenvalue lambda J is G sub J, the geometric multiplicity. Because the idea is each of these blocks corresponds to one eigenvector, and then the rest of these columns correspond to generalized eigenvectors. So just as the total number of blocks corresponds to the number of linearly independent eigenvectors, the number of blocks corresponding to one eigenvalue gives that geometric multiplicity. Another thing you can say is, suppose you take all the Jordan blocks for a particular eigenvalue. So the sum of the sizes of your Jordan blocks for a particular eigenvalue lambda J is equal to the algebraic multiplicity. So if you have a Jordan form, you can read off the algebraic and geometric multiplicity of each eigenvalue. So I'll give you an example to illustrate these multiplicities, and then discuss what's wrong with the Jordan form. I think I'll just be able to finish this in time. Jordan form for our matrix A looks like this. So we have a 3 by 3 Jordan block for an eigenvalue 2. So we have a couple ones in the super diagonal. So that's one block. And then we have a 2 by 2 Jordan block with the eigenvalue 3. And then we have a 1 by 1 Jordan block that just has 2 in it. So for our eigenvalues, lambda 1 is 2, lambda 2 is equal to 3. These are the two distinct eigenvalues that we have. The geometric multiplicity of 2 is 2. Because we have two Jordan blocks that feature the eigenvalue 2 on the diagonal. Whereas the geometric multiplicity of the eigenvalue 3 is equal to 1, because we only have one Jordan block with 3 in the diagonal. As for the algebraic multiplicity, the algebraic multiplicity of 2 is the sum of the sizes of these blocks, 3 here and 1 here, so we get 4. And then here we have just a 2 by 2 block for the eigenvalue 3, so that algebraic multiplicity is 2. So these have to sum to the overall size of a matrix, that's 6. The algebraic multiplicities must sum to n. But not the geometric. So both eigenvalues are defective. So this matrix is totally not diagonalizable. In fact, how many 1s you have on the super diagonal tells you how many generalized eigenvectors you have in total. 3 in this case. So if you were to form a matrix X, so that A is X, J, X inverse, X would have 3 linearly independent eigenvectors and then 3 generalized eigenvectors to complete the whole space. Okay. So any questions about this example and what it says about multiplicities?
Yeah, let me just make sure I understand. So M1 plus M2, it has to equal 6. Is that
yeah, it has to equal the size of a matrix.
Okay, so then what did you say after? How do you know that it has 3 eigenvectors and 3 generalized eigenvectors?
Oh, it's just because if you sum the geometric multiplicities, you get the total number of regular eigenvectors.
Okay.
And then n minus that is the number of generalized.
Okay.
Which is also equal to the number of 1s. Any other questions? All right. The last point I'll make is, it'd be nice if we could go ahead and compute a Jordan form, because that would tell us everything. But here's the problem. We can never, ever reliably compute the Jordan form of a matrix. At least not a matrix that is not diagonalizable. And the reason why is, let's suppose you're computing the eigenvalues by whatever means, and you want to use that to build a Jordan form. And let's suppose two of your eigenvalues are really close to each other. So let's consider a case where you have one eigenvalue that's equal to 2, and a second eigenvalue that is 2.0000001. Well, how do you know if these eigenvalues are really a repeated eigenvalue? Or maybe they're two distinct eigenvalues that just happen to be clustered really closely together. You don't know. Unless you have some outside information about the matrix, maybe that would indicate its eigenstructure. But, and the thing is, the two cases are entirely different. If they are distinct, they have two linearly independent, but are almost dependent eigenvectors. If they are repeated, then you might still have two linearly independent eigenvectors, or maybe one regular, one generalized. How can you really tell? And that makes all the difference. So the Jordan form how do you know if it's supposed to be 2 1x1 blocks or a 2x2 block that has a 1 in the diagonal? And that's a big difference. You're talking about the Jordan form having either a 0 here or a 1 here. In other words, the real reason why you cannot reliably compute the Jordan form is because the matrix J is not a continuous function of the entries of A. Any other decomposition we've seen, LU, Cholesky, sure, the diagonalization of A, if it is diagonalizable, all those decompositions that we've seen so far happen to be continuous functions of the entries of A. So a tiny change in A will result in some sort of, maybe not as small, but some reasonably sized change in the decomposition. That is not true of a Jordan form. The tiniest change in A could cause this entry to flip from a 0 to a 1. We can't have that in any numerical setting. So in other words, whatever Jordan form you might compute, you can't really trust it. So nobody bothers to compute that. I won't have time to get into perturbation theory. This is actually section 7.2, which I'll unfortunately have to skip. But one of the main points of that section is, if you have eigenvalues that are clustered very closely together, so they might be a repeated eigenvalue, that makes computation of eigenvectors, and actually the whole eigensystem, very difficult to compute. That kind of clustering leads to numerical instability. So we'd like to have some spread between the eigenvalues if we can. And if your matrix doesn't have that property, then computing anything about its eigensystem, even if it's diagonalizable, is still very difficult. Okay, and well, I've gone 1 minute past time. So we will continue talking about eigenvalues, well, actually for the rest of the semester, but that's in the next.